February 21st, 1940. A cramped laboratory, University of Birmingham, England. The vacuum pump hissed steadily as John Randall adjusted the magnet assembly around a crude copper cylinder sealed with wax. His colleague Harry Boot monitored the oscilloscope in the corner, watching for any sign of the electromagnetic oscillations they'd been chasing for months. Outside, the winter darkness pressed against blacked-out windows. Somewhere over the English Channel, German bombers were preparing for another night raid. The war Churchill had promised would be over by Christmas of 1939 showed no signs of ending. France would fall within 16 weeks. Britain would stand alone. And in this cluttered university laboratory, two physicists were about to create something that would change everything, though neither understood yet what they had accomplished. Boot's voice cut through the mechanical noise. "Randall, you need to see this." The oscilloscope trace had exploded into life. The copper cylinder, no larger than a coffee can, with 8 precisely machined cavities drilled into its surface, was generating microwave radiation at a frequency and power level that should have been impossible. 400 watts at 9.8 centimeters wavelength, 100 times more powerful than anything anyone had achieved at that frequency. The needle on the power meter trembled at readings that violated every assumption about what vacuum tube technology could accomplish. Randall stared at the readings, then at the device, then back at the oscilloscope. They had been trying to build a better radar transmitter, following instructions from a government desperate for any technological edge against the Luftwaffe. British fighter pilots were dying because existing radar could detect enemy bombers, but lacked the precision to guide accurate interception. The chain-home radar stations stretched along Britain's coast, operated at wavelengths measured in meters, which meant their antennas had to be enormous steel towers visible for miles. What the military wanted was radar that could fit inside an aircraft, that could see through darkness and clouds, that could detect a submarine's periscope from miles away. But microwave radar required power, and every previous attempt to generate sufficient microwave power had failed. The klystron tubes that American researchers had developed could barely produce 10 watts. British scientists experimenting with various magnetron designs had achieved perhaps 50 watts under laboratory conditions. 400 watts changed everything. Randall understood immediately that if this device could be manufactured, if engineers could figure out how to make it robust enough for military service, British radar would leap ahead of anything the Germans possessed. Boot understood something else. They had just made themselves and their copper cylinder the most valuable scientific assets in Britain, which meant they had also made themselves targets. Within hours, the results would be classified. Within days, military officials would arrive to examine their work. Within weeks, the device would be codenamed and its existence would become a state secret protected by armed guards and official lies. And within 6 months, a desperate Churchill would make the most audacious gamble of the war, shipping this British invention across the Atlantic to share with a neutral America, trusting that American industrial might could transform a laboratory curiosity into the weapon that would win the Battle of the Atlantic. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The path to that February morning had begun not in physics laboratories, but in the grim arithmetic of merchant ship losses. By early 1940, German U-boats were sinking British shipping faster than shipyards could replace the losses. Every torpedo that struck home cut Britain's lifeline to the resources needed to continue fighting. Food, fuel, weapons, raw materials, everything that kept Britain in the war had to cross the Atlantic past submarine wolf packs that hunted with increasing effectiveness. The mathematics were brutal and undeniable. At current loss rates, Britain would be starved into submission before German tanks ever crossed the Channel. Admiral Karl Dönitz, commander of Germany's submarine force, understood this perfectly. He didn't need to invade Britain. He simply needed to sink 600,000 tons of shipping per month consistently, and Britain's reserves would drain away. The island nation would face a choice between starvation and surrender, and in 1940, Dönitz had only 30 operational U-boats. He had requested 300. Hitler, focused on land warfare and the coming invasion of France, had refused. But even with this limited force, the U-boats were winning. In March 1940, they sank 23 merchant ships. In April, 12. In May, 13. Not enough to force British surrender, but enough to demonstrate what a larger submarine fleet might accomplish. British convoys sailed across the Atlantic protected by escort vessels, equipped with ASDIC, an early form of sonar that could detect submerged submarines under ideal conditions. But ASDIC had severe limitations. It worked poorly in rough seas, it couldn't detect submarines on the surface, and it gave no warning of submarines lurking beyond visual range. What the Royal Navy desperately needed was a way to detect surfaced submarines at night when the U-boats were most dangerous. Submarines of that era spent most of their time on the surface, diving only to attack or evade pursuers. They were faster on the surface, running on diesel engines that also recharged batteries. They could see farther, navigate more easily, and communicate with their commanders. At night, a surfaced submarine was nearly invisible to surface ships. But it would be perfectly visible to radar if anyone could build radar powerful enough and portable enough to mount in patrol aircraft. That was the problem Randall and Boot had been sent to solve. The British Air Ministry had established precise requirements. The radar needed to operate at 10 centimetre wavelength to allow reasonably sized antennas. It needed at least 1 kilowatt of transmitted power to detect small targets at useful ranges, and the transmitter needed to be compact enough to fit in an aircraft. By early 1940, British researchers had concluded these requirements were probably impossible to meet simultaneously. American scientists studying the same problems had reached the same conclusion. German engineers had given up entirely on centimetric radar, declaring it theoretically possible but practically worthless for military applications. They had focused instead on improving their metric wavelength radar and developing electronic countermeasures. This German decision would prove catastrophic. Randall and Boot succeeded where others had failed, partly through insight and partly through desperation. They were not trying to improve existing magnetron designs through incremental refinement. They were attacking the fundamental problem from first principles. Mark Oliphant, the physicist directing Britain's radar research, had given them a simple instruction: find a way to generate kilowatt-level microwave power, or accept that Britain would lose the war for lack of detection capability. Randall's key insight was to abandon the external vacuum envelope used in conventional radio tubes and instead build the resonant cavities directly into a solid metal block. This allowed much better heat dissipation, which was the primary limitation in previous high-power magnetron designs. They machined cylindrical cavities into a copper block, arranged symmetrically around a central hole that would contain the cathode. The Ferrier side, cavities acted as resonators, like organ pipes tuned to specific frequencies. When electrons accelerated by magnetic fields spiraled past these cavities, they would induce electromagnetic oscillations at microwave frequencies. In theory, in practice, the device might do nothing, or it might arc over and destroy itself, or it might oscillate at useless frequencies, or it might achieve some modest improvement over existing designs. What it actually did was generate 400 watts at exactly the wavelength they needed on the very first test, with a device that cost perhaps £10 in materials and could be machined in an afternoon. The implications were staggering. This was not a laboratory curiosity requiring months of careful adjustment by expert technicians. This was a practical device that could potentially be manufactured in quantity. British officials immediately understood they possessed something extraordinary. But Britain in 1940 lacked the industrial capacity to exploit this breakthrough. The island nation was mobilized for immediate survival. Every factory was producing fighters, bombers, tanks, guns, ammunition, the material needed to resist German invasion. There was no excess capacity for radar production on the scale required, and no time to build new factories while German bombs destroyed existing ones. The solution would require trust, diplomacy, and enormous courage. Churchill would have to share Britain's most valuable secret with a neutral America, hoping that American factories could mass-produce the magnetrons that Britain desperately needed but could not manufacture itself. The decision was not made lightly. Sharing advanced military technology with a neutral power violated every instinct of wartime security. What if America decided to remain neutral and sold magnetrons to Germany? What if American companies stole the technology and refused to share the resulting products? What if the secret leaked to German spies operating in America? These were not theoretical concerns. American neutrality in 1940 was genuine and deeply rooted. Powerful political forces opposed any American involvement in Europe's war. Roosevelt sympathized with Britain but faced severe domestic constraints on how much assistance he could provide. And German intelligence operated extensively throughout the United States, with access to American industry and universities. Churchill calculated that the risks of sharing the magnetron were less than the certainty of defeat without it. In the spring of 1940, he authorized planning for what would become the Tizard mission, a delegation of British scientists who would travel to America carrying Britain's most closely guarded technical secrets. The mission would be led by Henry Tizard, the physicist who had championed radar development before the war and who had Churchill's complete confidence. Tizard's instructions were explicit. Offer the Americans everything: the cavity magnetron, radar system designs, radio proximity fuse specifications, jet engine details, even preliminary calculations on atomic weapons. Hold nothing back. Demonstrate complete trust, and hope the Americans would reciprocate. The gamble was that American industrial capacity, once engaged, would produce weapons and equipment in quantities that would overwhelm German production. But first, the Americans had to be convinced that British technology was worth the investment. They had to see that the cavity magnetron was not just marginally better than American research, but represented a revolution in microwave engineering. They had to understand that radar would be decisive, and that Britain held the key technology. This would require careful demonstration and diplomatic skill. American scientists and military officials would need to be persuaded that collaboration offered benefits beyond simple military aid to Britain. They would need to see how cavity magnetron technology could advance American research programs that were currently stalled by the same power generation problems Britain had just solved. The stage was set for one of the most consequential technology transfers in history. In August 1940, while the Battle of Britain raged overhead, a small group of British scientists would board a ship for Canada, carrying a locked metal case containing documents and devices that would change the trajectory of World War II. Among those items would be cavity magnetron serial number 12, the 8th prototype manufactured by General Electric Company in Wembley, featuring 8 resonant cavities machined into a copper block weighing perhaps 2 pounds. That copper block would turn out to be worth more than its weight in gold, uranium, or any other material on Earth. It would be the key that unlocked America's industrial might and transformed the Atlantic from a German hunting ground into an Allied lifeline. September 19, 1940. The Wardman Park Hotel, Washington, D.C. Edward Taffy Bowen carefully removed a cylindrical object from the metal box he had carried across the Atlantic. The device was wrapped in protective material, small enough to hold in 2 hands, utterly innocuous in appearance. Around the hotel suite's conference table sat some of America's most prominent scientists and military officials. Vannevar Bush, recently appointed to coordinate American defense research; Alfred Loomis, the wealthy physicist who had converted his private estate into an advanced radar laboratory; Carl Compton, president of MIT and member of the National Defense Research Committee. Several Navy representatives who had arrived were skeptical that the British possessed anything worth seeing. The meeting had not started well. There had been cautious probing on both sides, each delegation wary of giving away information without receiving something valuable in return. The British had described their chain-home radar network, the meter wavelength early warning system that had proven crucial during the Battle of Britain. The Americans had listened politely, then revealed that the US Navy had developed virtually identical technology independently. Both sides had described their microwave research programs and found they were pursuing similar approaches with similar limited results. The British had realised that Bell Telephone Laboratories and General Electric possessed receiver technology potentially superior to British designs. The Americans had admitted that their shortwave radar program had hit a dead end due to insufficient transmitter power. Loomis had described the problem in frank terms. His laboratory at Tuxedo Park had been working on microwave radar for months. They could build receivers, they could design antennas, they could create display systems. But they could not generate enough microwave power to make the system practical. Their klystron tubes produced about 10 watts, barely enough for laboratory demonstrations, completely inadequate for detecting targets at useful ranges. Unless someone solved the power generation problem, microwave radar would remain a theoretical curiosity. Bowen had listened to this recitation carefully. Then he unwrapped the cavity magnetron and placed it on the conference table. "This device," he said simply, "produces 1,000 times the power you just described." The room went completely silent. Bowen explained the specifications: 10 centimeter wavelength, 10 kilowatts peak power in the prototype, with production versions achieving higher outputs, compact enough to fit in an aircraft, robust enough for military service, already being manufactured in Britain, though in limited quantities due to industrial capacity constraints. The Americans studied the device with expressions ranging from disbelief to awe. It looked too simple. A copper cylinder with holes drilled in it, some mounting hardware, cooling fins. This could generate 10 kilowatts of mounting. Microwave power? Impossible. Bell Telephone Laboratories had the best radio engineers in the world, and they considered microwave power generation an unsolved problem. How could the British have achieved 100-fold improvement using what appeared to be crude mechanical construction? Loomis asked for proof. Bowen arranged for the magnetron to be tested at the General Electric Laboratory in New Jersey within days. When the device was energized and the instruments confirmed its specifications, the skepticism evaporated instantly. The Americans immediately understood what the British had brought them. This was not a marginal improvement over American research. This was a revolution. With this technology, microwave radar became practical for every application the military had imagined but considered unfeasible. Airborne interception radar to guide night fighters against German bombers. Ground mapping radar to allow bombers to navigate and identify targets through clouds. Ship-based search radar to detect submarines at night. Gun-laying radar to direct anti-aircraft fire with unprecedented accuracy. Every one of these applications depended on having a compact, powerful microwave transmitter, and the British had just handed the Americans the solution. The military and industrial implications were immediately obvious to everyone in that hotel suite. The man who perhaps understood the consequences most clearly was not a scientist or military officer, but a historian. James Finney Baxter III would later write that when the Tizard mission brought the cavity magnetron to America in 1940, they carried the most valuable cargo ever brought to our shores. The judgment was not hyperbole. The cavity magnetron would enable radar systems that would prove decisive in multiple theatres of World War II. It would allow Allied aircraft to detect and sink German submarines that had previously operated with near impunity. It would guide night fighters that would break the German night bombing campaign against Britain. It would provide the navigation systems that made strategic bombing of Germany practical in all weather conditions. It would detect German Von-flying bombs in time for anti-aircraft guns to shoot them down over the English Channel. Each of these applications would save thousands of Allied lives and shorten the war by months or years. But all of that lay in the future. In September 1940, what mattered was that American officials had seen proof that British technology was genuinely ahead of American research in a critical area, and that British scientists were willing to share that technology completely and without reservation. This demonstration of trust would catalyze an unprecedented level of technical cooperation between Britain and America. Within weeks, MIT would establish the Radiation Laboratory, deliberately given a misleading name to conceal its true purpose of developing practical radar systems based on the cavity magnetron. The laboratory would eventually employ nearly 4,000 scientists and engineers, becoming one of the largest military research projects of the war. But even more critical than the research would be manufacturing. The British had proven that the cavity magnetron worked. Now American industry needed to figure out how to produce it in quantities measured in hundreds of thousands rather than dozens. This would require solving a different set of problems. The British prototypes were handcrafted by skilled machinists, each unit requiring days of careful work. Mass production would require completely different manufacturing approaches, automated processes, standardized components, quality control methods that could detect defects before devices failed in combat. No one in that Washington hotel suite understood yet how difficult this would prove or how critical American manufacturing innovation would become. The cavity magnetron represented a scientific breakthrough, but science alone does not win wars. What wins wars is the ability to transform scientific discoveries into weapons manufactured in overwhelming quantities and deployed effectively across multiple theatres of operation. The British had won the scientific race. The Americans were about to win the industrial race, and Germany, confident in its technical superiority and dismissive of Allied capabilities, was about to discover that the Battle of the Atlantic had changed in ways German commanders would not understand until it was far too late. March 1943. Bay of Biscay. Atlantic approaches. U-boat commander Kapitänleutnant Hans-Joachim Schwantke brought U-435 to the surface after 16 hours submerged, crossing the dangerous transit zone where RAF Coastal Command aircraft hunted submarines attempting to reach the Atlantic operational areas. It was a moonless night, conditions that should have provided perfect cover. The watch officer scanned the horizon with binoculars while the diesel engines coughed to life, recharging batteries depleted by the long underwater passage. The Metox radar detector sat silent in the radio operator's headphones. No warning. Nothing but the ambient noise of radio static. Then searchlights blazed from directly overhead. A Wellington bomber had been circling the exact position where U-435 surfaced, waiting with its new ASV Mark III radar that the Metox could not detect. Depth charges fell as the crew scrambled to crash dive. The boat survived, barely, limping back to port with a pressure hull cracked by near misses that had come within seconds of imploding the submarine entirely. Schwantke's war diary entry was terse but captured the essence of what had changed. We were blind. The Metox gave no alarm. The aircraft appeared as if materialized from darkness itself. Either the British have developed radar our detectors cannot sense, or they are using technology we do not understand. That same scene was repeating itself across the Atlantic with horrifying frequency. U-boats that had operated with confidence through late 1942 were suddenly being caught on the surface without warning, bombed before they could dive, hunted by aircraft that seemed to possess supernatural detection capabilities. The statistics told a story that German naval commanders struggled to comprehend. In November 1942, U-boats had sunk approximately 119 merchant ships worldwide while losing 13 submarines. In December, 60 merchant ships sunk for 5 U-boats lost. January 1943 saw 37 merchant ships sunk and 7 U-boats destroyed. The exchange ratio that had favoured Germany was deteriorating month by month. February brought 34 merchant ships sunk and 17 U-boats lost. Something fundamental had changed in Allied detection capabilities, but German scientists could not determine what. Admiral Karl Dönitz, promoted to Commander-in-Chief of the entire German Navy on January 30, 1943, watched these numbers with mounting alarm. His U-boat headquarters in Paris maintained detailed plots of every engagement, every loss, every mysterious detection. The patterns made no sense according to existing understanding of radar technology. U-boats approaching convoys in total darkness were being intercepted before they could attack. Boats transiting the Bay of Biscay at night were being bombed with precision that visual detection could not explain. Submarines running submerged during daylight were somehow being tracked and depth-charged. The weather during many attacks ruled out visual detection entirely, yet the attacks came with devastating accuracy. Dönitz convened emergency meetings with Germany's top radar scientists throughout January and February. The discussions revealed disturbing ignorance about Allied capabilities and troubling complacency about German technological superiority. German experts insisted that effective radar could not operate at wavelengths shorter than about 50 centimeters due to fundamental power generation limitations. The klystron tubes that represented the state-of-the-art in German microwave technology could barely generate 20 watts at those frequencies. That was adequate for laboratory experiments, but useless for military applications requiring detection at useful ranges. The METOX radar warning receivers, designed to detect Allied radar operating at meter-and-a-half wavelength, should theoretically provide warning of any radar-equipped aircraft. Yet clearly they were not providing adequate warning anymore. Some German scientists speculated that the Allies had developed infrared detection systems that could sense heat from U-boat diesel exhaust. Others suggested acoustic detection, though this seemed implausible at the operational distances involved. A few voices mentioned the theoretical possibility of centimetric radar using advanced magnetron technology, but this was dismissed as impractical. Germany's own research into such systems had concluded they offered no tactical advantage worth the enormous development investment required. If German engineers, widely regarded as the best in the world, had determined that centimetric radar was impractical, then surely it must be impractical. The British, suffering under years of strategic bombing with their industrial base under constant attack, could not possibly have developed revolutionary radar technology superior to anything Germany possessed. The idea seemed absurd to German experts confident in their nation's scientific leadership. This confidence was about to shatter completely. February 2nd, 1943. The night sky over Cologne glowed orange with fires from the latest RAF bombing raid. Short Stirling bomber R9264 from No. 7 Squadron climbed away from the target area, its H-2S ground mapping radar still operating, the rotating an antenna beneath the fuselage, scanning the landscape below and presenting a map-like image on the operator's cathode ray display. This was only the system's second operational use. The radar was so secret that Churchill himself had agonized over authorizing its deployment, fearing exactly what was about to occur. A German night fighter spotted the Stirling illuminated against the burning city. Cannon fire tore through the bomber's port wing. The aircraft went into a steep dive, the crew unable to regain control. It crashed near Rotterdam in the occupied Netherlands, killing all 7 crew members instantly. German security forces reached the crash site within hours. Among the wreckage, they found equipment unlike anything they had encountered before. The rotating antenna assembly, the cathode ray display system, the sophisticated power supply, and most critically, a transmitter assembly containing a device that would explain every mysterious U-boat loss of the past months. The cavity magnetron was recovered nearly intact. German technicians carefully extracted it from the wreckage and transported it under armed guard to Telefunken headquarters in Berlin. General Wolfgang Martini, chief of Luftwaffe Signals Intelligence and one of Germany's most senior radar experts, was alerted immediately. As the officer responsible for all German radar development, Martini understood that this Rotterdam find might provide answers to questions that had been haunting German commanders for months. On February 23, 1943, a working group assembled at Telefunken's Berlin offices to examine what the Germans designated the Rotterdam Gerät, the Rotterdam apparatus. The magnetron itself was a copper cylinder, approximately 8 centimeters in diameter, with 8 cylindrical cavities precisely machined into its surface. Permanent magnets surrounded the assembly. It appeared deceptively simple, almost crude compared to the elegant vacuum tube designs German engineers had developed. Initial laboratory tests revealed its extraordinary capabilities. The device generated enormous microwave power at frequencies German equipment could neither produce nor reliably detect. When the German engineers energized the magnetron using laboratory power supplies, the frequency counter registered 3.3 GHz. The wavelength was 9.1 centimeters. The power output measured 40 kilowatts peak. These numbers explained everything and devastated every assumption German commanders had made about the technological balance of the war. The Metox warning receiver was designed to detect radar operating around 1.5 meter wavelength, approximately 200 MHz. The British Magnetron operated at 9.1 centimeter wavelengths, more than 16 times shorter. German warning receivers were completely blind to this radiation. U-boats had been running blind into enemy attacks, their defensive systems obsolete without their knowledge. The electromagnetic spectrum the British were exploiting was entirely outside the range German detectors could sense. Over the following weeks, Telefunken engineers worked around the clock to reverse engineer the complete H-2S system from recovered wreckage and components. They determined it was a ground-mapping radar system that scanned a full circle beneath the aircraft, displaying coastlines, cities, rivers, and terrain features with remarkable clarity on a plan position indicator. British bombers could navigate and identify targets in complete darkness or through solid cloud cover. The system had been designed primarily for strategic bombing navigation, but the implications for submarine warfare were even more profound. The same cavity magnetron technology, adapted for air-to-surface search radar designated ASV Mark III, could detect a submarine's conning tower from miles away in any weather, day or night. The small radar cross-section that had previously protected submarines from detection meant nothing against this sensitive high-frequency system. Worse, the microwave emissions were completely undetectable by existing German radar warning equipment. U-boats were visible to enemies they could not see until the moment searchlights blazed and depth charges fell. The February 23 meeting presentation was somber. While no documentary evidence confirms personal attendance by either Reichsmarschall Hermann Göring or Admiral Dönitz, both were certainly briefed on the findings. Representatives from every major German electronics firm attended. Senior Luftwaffe signals officers and naval technical specialists filled the conference room. The assessment was devastating. Germany could not replicate cavity magnetron production in operationally significant numbers before 1944 at the earliest. The precision machining, specialized copper alloys, powerful permanent magnets requiring cobalt that Germany lacked, and the manufacturing expertise were all beyond immediate German capabilities. Developing effective countermeasures would require at least 6 months. New radar warning receivers tuned to centimetric frequencies could theoretically be designed. But production and installation across the entire U-boat fleet would extend well into 1944. Most devastating, the British almost certainly had variants of this technology beyond what had been captured. The Rotterdam device operated at 9.1 centimeters. Allied scientists likely had already developed or were developing 3-centimeter systems that would render even new German countermeasures obsolete before deployment. The technological race was not merely lost. It was unwinnable in the war's current timeframe given the Allied head start and superior industrial capacity. Dönitz absorbed these briefings with a growing understanding of the catastrophe facing his command. Every advantage his U-boats had possessed was being systematically negated by Allied technology that had been deployed in overwhelming quantities while German scientists remained unaware it even existed. Surprise attack at night meant nothing when the enemy could see in complete darkness. The vast expanse of the Atlantic provided no concealment when radar could detect a conning tower from miles away. Radar warning systems gave false confidence while providing no actual protection. The question was stark. What could be done while German industry scrambled to develop countermeasures that might not arrive until 1944? Several tactical adaptations were implemented immediately. All U-boat commanders were informed that radar warning systems were unreliable and should not be trusted. Boats would remain submerged as much as possible, surfacing only when absolutely necessary to recharge batteries. Anti-aircraft armament would be increased, though everyone recognized this as a desperate measure against aircraft that could detect U-boats long before visual range. Most critically, Dönitz and his staff began preparing for the possibility that the U-boat campaign in the Atlantic might become unsustainable. If losses continued at current rates while Allied shipbuilding capacity expanded, the strategic mathematics would become impossible. March 1943 proved both the apex and the beginning of the end for the U-boat force. The largest convoy battles of the war were fought that month, with massive wolf packs attempting to overwhelm convoy defences through sheer numbers despite growing Allied technological advantage. Convoys HX-229 and SC-122, sailing together through the North Atlantic in mid-March, were attacked by approximately 40 U-boats from 3 wolf packs. The battle raged from March 16th to 20th. 21 merchant ships totaling 141,000 tons were sunk, the highest losses from any single convoy battle. Yet the cost to Germany was unsustainable. Multiple U-boats were damaged or destroyed, and the broader March statistics showed losses Germany could not afford. Allied losses for March totaled 120 ships of 693,000 tons worldwide, with 82 ships totaling 476,000 tons lost in the Atlantic. The U-boat arm lost 12 submarines during the month. More critically, American shipyards were producing merchant vessels faster than U-boats could sink them. The Liberty ship program had reduced construction time dramatically. While individual record-breaking ships captured headlines, even standard production rates meant American yards were launching ships continuously. German U-boats achieving typical wartime performance could not match this production. As long as Allied shipyards replaced losses faster than U-boats inflicted them, the campaign represented strategic defeat disguised as tactical success. The only way to win was to maintain an unsustainable exchange ratio while avoiding losses Germany could not replace. Then came May 1943, the month that would become known among U-boat crews as Black May. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Throughout May, Allied aircraft and surface escorts equipped with centimetric ASV Mark III radar and Type 271 shipboard radar savaged the U-boat force with unprecedented effectiveness. The convoy battle for ONS-5 in late April and early May marked the turning point. This slow convoy of 43 merchant ships, protected by 16 escorts, was attacked by approximately 30 U-boats. The Germans managed to sink 13 merchant ships, but they lost 6 U-boats with additional boats severely damaged. For the first time in a major convoy battle, U-boat losses approached their successes. The exchange ratio had become unsustainable. 2 weeks later, convoy SC-130 demonstrated and complete Allied dominance. Of approximately 37 merchant ships in convoy, 0 were lost despite attacks by more than 24 U-boats from 3 patrol lines. The German forces lost between 3 and 5 submarines. Among the dead was Oberleutnant Zursee Peter Dönitz, the admiral's youngest son, serving as watch officer aboard U-954. The boat was detected by the River-class frigate HMS Jed and B-class sloop HMS Sennen. British escorts prosecuted the contact with Hedgehog anti-submarine mortars that exploded only on contact, confirming hits rather than simply disturbing the water. U-954 was destroyed with all 47 crew members killed. The loss was reported to Admiral Dönitz by secure telegraph. His youngest son was gone. Dönitz did not pause operations or take leave. There would be time for grief after the war, if Germany survived. For now, his duty was to the approximately 40,000 submariners under his command, the living who still depended on his decisions. Throughout May, the losses mounted relentlessly. U-boats were being destroyed faster than training schools could replace experienced crews. By May 22nd, 41 to 43 boats had been lost during the month, depending on classification methodology. The losses represented approximately 25% of operational U-boat strength. It was catastrophically unsustainable. On May 24, 1943, Dönitz made the most painful decision of his career. He drafted the order that effectively conceded defeat in the Battle of the Atlantic. To all U-boats at sea, due to superiority of enemy location equipment and overwhelming air coverage, North Atlantic operations are temporarily suspended, effective immediately. All boats currently in the North Atlantic are to withdraw to positions southwest of the Azores. The immediate statistical impact was dramatic. In June 1943, only 17 merchant ships were sunk in Atlantic. In July, only 9. The Allied supply line that had seemed on the verge of being severed in March became secure. The vast convoys that would support D-Day and the liberation of Europe began assembling in American ports, protected by technology that had rendered Germany's most effective weapon obsolete. But the human toll on the U-boat force continued throughout the remaining years of the war. Of the approximately 40,000 men who served in U-boats during the conflict, approximately 28,000 to 30,000 would die, representing a casualty rate of approximately 75%. This was the highest casualty rate of any military service on either side of the war. They drowned in steel cylinders crushed by depth charges. They suffocated when air systems failed under prolonged attack. They burned when diesel fuel ignited from combat damage. They froze in the North Atlantic after their boats were sunk. They died knowing their equipment was inferior, their missions increasingly futile, their sacrifice changing nothing in the war's strategic outcome. Yet they continued fighting because duty demanded it, because abandoning the struggle would free Allied forces for other theatres, and because the alternative was admitting that the war was already lost. The interrogation reports from captured U-boat crews during summer and fall 1943 revealed the profound psychological impact of technological inferiority. Allied intelligence officers, initially confused by the defeatism among prisoners who had been fanatical believers in German victory just months earlier, gradually recognized they were witnessing something unique. These men had not been defeated in conventional battle. They had been rendered obsolete by science, hunted by technology they could neither see nor counter. The psychological documentation from German naval personnel provides perhaps the most compelling evidence of the cavity magnetron's war-winning impact. These were not defeated soldiers seeking excuses for failure. They were highly trained specialists who understood exactly what had gone wrong. Their testimony, recorded in interrogation reports and post-war memoirs, consistently emphasized not tactical errors or operational failures, but fundamental technological obsolescence. They described the helplessness of fighting enemies who possessed superior detection capabilities, while German forces remained effectively blind. They explained the fatalism that infected crews who knew detection was inevitable, and survival largely a matter of luck rather than skill. They documented the transformation from confident warriors to hunted prey, a psychological shift that occurred not through battlefield defeat, but through technological revelation. The technical investigations continued through 1943 and 1944 as German engineers desperately attempted to develop countermeasures. They produced limited quantities of their own cavity magnetrons, copying the British CV-64 design. But production was severely constrained by material shortages, particularly the cobalt required for permanent magnets. Most early units required magnets salvaged from captured aircraft equipment, making large-scale production impossible. Telefunken began developing an indigenous German magnetron, but it would not reach even limited production until April 1944, far too late to affect the war's outcome. Radar warning receivers that could detect centimetric frequencies were developed in parallel efforts. The Naxos system was introduced in September 1943. It could theoretically warn U-boats of approaching aircraft equipped with ASV Mark III radar operating at 9.1 cm wavelength. However, by the time Naxos entered operational service, Allied scientists had already deployed 3 cm radar systems against which Naxos was blind. The Germans were perpetually one generation behind, forever, attempting to counter yesterday's threats, while new systems rendered their countermeasures obsolete before wide deployment. The German Navy attempted tactical adaptations to cope with Allied radar superiority. U-boats were fitted with additional anti-aircraft guns. Some boats became designated flak boats carrying heavy armament. The theory was that if submarines could not hide from radar-equipped aircraft, they should remain surfaced and fight with anti-aircraft fire. This proved disastrous in practice. Allied aircraft could detect U-boats from ranges far exceeding effective anti-aircraft fire. The aircraft's speed advantage meant it could choose when and how to attack. Radio transmissions from aircraft under attack brought reinforcements. The flak boat program cost more submarines than it destroyed aircraft, representing another failed attempt to counter Allied technological advantage through tactics alone. Acoustic homing torpedoes, codenamed Zornkönig and designated G7ES or T5, were introduced in September 1943 as a countermeasure against convoy escorts. These torpedoes could home in on propeller noise of escort vessels. Initial results were promising. However, the Allies quickly developed countermeasures, including the Foxer noisemaker towed behind ships to decoy the acoustic torpedoes. More fundamentally, acoustic torpedoes could not compensate for the inability to locate convoys in the first place. If Allied radar detected U-boats before they could approach convoys, acoustic torpedoes provided no advantage. New submarine designs incorporating snorkel systems represented another adaptation attempt. The snorkel, originally a Dutch invention from 1938, captured when Germany overran the Netherlands, allowed boats to run diesel engines while submerged at periscope depth, recharging batteries without surfacing. This reduced vulnerability to radar-equipped aircraft. However, snorkels left a wake visible to radar, particularly in calm seas. They limited speed to a few knots. They required excellent seamanship in rough weather. By mid-1944, approximately half of U-boats operating from French bases were snorkel-equipped. While this improved survival rates somewhat, it could not reverse the fundamental strategic defeat. The revolutionary Type 21 electroboat represented Germany's most ambitious attempt to regain technological parity. This radical design featured streamlined hull form, triple battery capacity, 17.2 knots submerged speed compared to 7.6 knots for conventional Type 7 boats, 6 bow torpedo tubes with hydraulic reload capability, allowing 18 torpedoes to be fired in under 20 minutes, and sophisticated sonar systems. The Type 21 could theoretically outrun most surface escorts while submerged and remain underwater for extended periods. Had this design entered service in 1943, it might have significantly extended the Battle of the Atlantic. However, rushed production created severe quality problems. Of 118 boats constructed, only 4 were fully combat-ready before war's end. Only 2 conducted combat patrols in April and May 1945, achieving no sinkings before Germany's surrender. The final U-boat patrol of the war demonstrated both the potential and the futility of German technological efforts. U-2511, the first Type 21 to see operational service, departed on April 30, 1945, commanded by Korvettenkapitän Adalbert Schnee, one of Germany's most experienced commanders. On May 4, U-2511 detected a British cruiser task force and executed a perfect attack approach, reaching firing position undetected despite Allied radar coverage. The boat's superior underwater speed and silent running capabilities allowed it to close to attack range without detection. Schnee did not fire. Germany had announced surrender, negotiations. He surfaced and radioed his position on May 5, 1945, ending the U-boat war not with violence but with acceptance of defeat. The statistical summary of the Battle of the Atlantic confirms the decisive impact of the cavity magnetron's introduction. From January through May 1943, during the period when first-generation ASV Mark III radar was being deployed but before full operational coverage was achieved, U-boats sank 245 merchant ships, totaling approximately 1,289,000 tons. German losses during this period were 95 U-boats, including the catastrophic 41 to 43 boats lost in May alone. From June 1943 through May 1944, after centimetric radar equipped most Allied aircraft and ships operating in the Atlantic, merchant ship losses dropped to 185 ships, totaling approximately 819,000 tons, despite more U-boats being at sea. German losses during this period climbed to 237 U-boats. The exchange rate had reversed completely. In March 1943, at the peak of U-boat effectiveness, Germany sank 82 merchant ships, totaling 476,000 tons in the Atlantic, while losing 12 submarines. By summer 1943, typical months saw fewer than 20 merchant ships sunk, while U-boat losses remained in double digits. The tonnage war had become unwinnable. The May 1943 convoy battles represented Germany's last chance to achieve strategic success in the Atlantic. The examination of the Rotterdam device in February 1943 had confirmed what many German commanders suspected but hoped was not true. Allied technological capabilities had advanced far beyond German understanding, creating detection advantages that no amount of tactical skill or operational courage could overcome. The post-war examination of captured U-boats by Allied technical teams revealed desperate German attempts to adapt through improvised countermeasures. Some boats had been covered with experimental radar-absorbent materials, crude attempts at stealth that added weight, reduced performance, and provided negligible reduction in radar returns. The materials available to Germany in 1943 and 1944 were inadequate for effective radar absorption at centimetric wavelengths. Others carried inflatable decoy balloons designed to create false radar targets, devices that sometimes worked but could not be deployed when submerged or in heavy seas. Still others had been fitted with modified exhaust systems designed to minimize the radar signature of snorkel emissions, modifications that reduced diesel efficiency without eliminating radar detection. Each adaptation represented German engineering ingenuity applied to an essentially unsolvable problem. You cannot hide from electromagnetic radiation using mechanical solutions alone. The physics were unforgiving. Allied radar operated at wavelengths and power levels that made submarines visible regardless of weather, darkness, or evasive maneuvers. The psychological documentation from German naval personnel provides perhaps the most compelling evidence of technological defeat. When Oberstleutnant Wilhelm Rung examined the Rotterdam device in February 1943, he performed an autopsy on German naval strategy. The copper block on his laboratory bench explained every mysterious U-boat loss, every impossible aircraft interception, every convoy battle where Allied forces seemed to know German positions before attacks developed. The cavity magnetron revealed that Germany had been fighting the Battle of the Atlantic while deaf and blind to the electromagnetic spectrum that Allied forces exploited with devastating effectiveness. That revelation, more than any military defeat, shattered German confidence in technological superiority and strategic victory. It convinced German leadership that Allied technological capabilities exceeded German understanding, not just in radar, but potentially across multiple domains. If the British could develop revolutionary radar systems in secret while enduring years of strategic bombing, what other surprises might they deploy? This psychological effect, the destruction of confident certainty about German technological superiority, influenced German defensive preparations throughout the remaining war years. By autumn 1943, production models of Allied centimetric radar equipped hundreds of aircraft and ships. The Type 271 naval radar using cavity magnetron technology was installed on convoy escorts, allowing them to detect surfaced submarines at ranges exceeding 12 miles and periscopes at approximately 900 yards. The ASV Mark III airborne radar equipped RAF Coastal Command aircraft, enabling them to patrol thousands of square kilometers and detect U-boats regardless of visibility conditions. The American H-2X radar, an advanced version of H-2S operating at 3 cm wavelength, provided bomber crews with navigation and targeting capabilities that rendered weather and darkness irrelevant to strategic bombing operations. Each system descended from the same revolutionary cavity magnetron technology that Runge had examined in February 1943. The Rotterdam device had been the key that unlocked Allied electromagnetic dominance across the entire theatre of operations. German attempts to counter this advantage consumed enormous resources for minimal operational effect. The final accounting of the Battle of the Atlantic tells a story of industrial capacity and technological innovation, overwhelming tactical skill and operational courage. Germany commissioned approximately 1,181 U-boats during World War II. Of these, 785 were destroyed, with 648 lost to enemy action and the remainder scuttled, lost to accidents, or stricken from service. Only 156 survived to surrender in May 1945. Of the approximately 40,000 men who served in U-boats during the war, approximately 28 to 30,000 died. These men fought with extraordinary courage and skill, but courage and skill could not overcome the fundamental technological disadvantage created by Allied radar superiority. The cavity magnetron, invented at Birmingham University in 1939 and 1940 and developed for practical military applications, represented one of the most significant technological breakthroughs of World War II. Its impact extended far beyond immediate military applications. The microwave technology developed for military radar became the foundation for post-war communication systems, television broadcasting, satellite communications, and eventually the microwave ovens found in kitchens worldwide. The industrial expertise developed for magnetron production enabled the electronics revolution of the 1950s and 1960s. The Anglo-American technological cooperation, exemplified by the Tizard mission's sharing of magnetron technology in 1940, established patterns of scientific collaboration that continued through the Cold War and beyond. The decision to deploy revolutionary technology, despite capture risks, influenced military technology policy for decades. The cavity magnetron demonstrated that operational advantage from advanced technology outweighed the risks of enemy exploitation, provided that industrial capacity could produce the technology in quantities the enemy could not match. For the German U-boat force, the story ended in surrender and scuttling. On May 4, 1945, Grand Admiral Dönitz, briefly serving as German head of state after Hitler's suicide, ordered all U-boats to cease offensive operations. On May 8, after Germany's unconditional surrender, boats still at sea were ordered to surface, fly black flags, and proceed to designated Allied ports. Many commanders instead scuttled their boats, unwilling to surrender the vessels in which their comrades had died. Over 200 U-boats were deliberately sunk by their own crews rather than surrendered to Allied forces. The men who had served in those boats, the 75% who died and the 25% who survived, had fought a campaign decided not by courage or tactics but by physics and engineering. They had been defeated by electromagnetic radiation generated by a block of copper machined in British factories, installed in Allied aircraft and ships, deployed in quantities German industry could never match. The examination of one captured radar set in February 1943 had explained their doom, revealing the electromagnetic dimension of warfare in which Germany had been fighting blind while the Allies possessed clear vision. The statistical evidence and the technological analysis both pointed to the same conclusion. The cavity magnetron had turned the tide of the Battle of the Atlantic more decisively than any tactical innovation or strategic decision. When Allied scientists celebrated the magnetron's impact after the war, they often referenced remarks about its decisive contribution. The cavity magnetron, they noted, won the Battle of the Atlantic, contributed to the air battle over Germany, and ultimately helped win the war. While this simplified complex historical causation involves many factors, the technical evidence provided strong support for the magnetron's crucial contribution. Without centimetric radar, Allied convoy losses would likely have remained at unsustainable levels throughout 1943 and into 1944. Without radar-equipped aircraft providing coverage, U-boats would have continued operating with relative impunity. Without the detection advantage magnetron technology provided, D-Day preparations would have been vulnerable to submarine interdiction. The magnetron, derived from fundamental research at Birmingham University, manufactured in tens of thousands of units across American and British factories, deployed widely enough to provide persistent coverage, had created an electromagnetic advantage that tightened inexorably around German naval forces until they could no longer operate effectively. In the end, the story of the cavity magnetron transcends the specific narrative of radar technology or submarine warfare. It represents the decisive advantage that advanced technology provides when deployed at industrial scale against opponents who lack the scientific knowledge, industrial capacity, and material resources to match or counter it. It demonstrates the psychological impact of fighting enemies who possess capabilities you cannot match, transforming confident warriors into hunted prey through the revelation of technological inferiority. Most fundamentally, it illustrates how a block of copper, 8 centimeters in diameter, precisely machined with 8 resonant cavities arranged around a central cathode, changed the course of history by making the invisible visible and the hidden exposed. The German admirals and scientists who examined that captured radar set understood perhaps more clearly than anyone else that they were witnessing not just Allied technological ingenuity, but the instrument of German defeat. The mathematics were irrefutable, the physics unforgiving, the strategic implications inescapable. They fought on because duty demanded it, and hope died slowly. But they knew. The examination of a single device had shown them the future. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.